Hello students, this is a video about vector components. In the drawing there are three vectors labeled vector A, vector B, and vector C, and we're going to calculate the components of all three of them. They don't represent anything in particular. They could be any quantity that's a vector. For instance, they could be a force or a displacement. It's not really important what they represent. At this moment, I'm just focusing on the skill of calculating vector components. So vector A is 44 units at an angle of 28 degrees from 0 degrees. We always go counterclockwise from 0 degrees unless there's some special circumstances. Same as in math class. So the vector components would represent how far to the right and how far up this vector A goes. So we typically dash, let me get a heavier line if possible. We typically dash our vector components because they're not really there. We're using math to calculate them. If this is a displacement, the object was displaced from here to here. We don't know exactly that it followed this path and this path, the two paths I just drew. All we know is the displacement, let's say. So let's say that this vector is the horizontal component, so I'll label that AX, and this vector, this dashed arrow that I drew, is the vertical component, AY. Now these are scalar components. We've broken this vector down into two scalars, so they're not quite the same thing as a vector, so I don't put the little arrow that's right there on them. Okay, first thing to do is to remember some trigonometry. If this is our angle of interest, we might call that theta, and then this side would be the adjacent side. The AX side is the adjacent side, and the AY side is the opposite side. And then the A vector side is the longest side of the triangle, the hypotenuse. If I'm going to calculate these vectors, these scalar components, then I'm going to use trigonometry. So remember that cosine of theta is always equal to the adjacent over the hypotenuse. And I know that 28 degrees is theta and 44 units is the hypotenuse. So I can rewrite that down, let me expand, rewrite that down below and calculate the length of scalar component AX, the horizontal component, using that. Sine theta is always equal to opposite over hypotenuse. So I can use that to calculate AY. In a typical situation, you're going to use cosine theta to calculate the horizontal component, or X component sometimes, and sine theta to calculate the Y component. But you can't always count on that. Sometimes it's different because a different angle is given. Remember that this is always a right angle by definition, or you can't use sine and cosine straightforwardly to calculate these. So I'll calculate AX down here. AX, well, I'll start over, my bad. We'll start from the beginning. Cosine of 28 degrees, make sure your calculator's in degrees while you're doing this, equals AX over 44.0 units, because that's given. So that means that using algebra, AX must equal 44 times the cosine of 28 degrees. I have a calculator, so give me a moment. But first, I got to check and make sure I'm in degrees, and I am. I get 38.849 something. So I'm just going to call that 38.85 units. It's usually okay to give an extra digit in the midst of your calculations. Later you might want to round off, but I'm going to leave that extra digit for now. And then I'm similarly going to calculate AY using sine of 28 degrees. Sine of 28 degrees is equal to AY over 44.0 units, meters, newtons, something. And that means that AY, not equal to AY is equal to 44 times the sine of 28 degrees. And that is 20.657 units. So I'll call that 20.66. Now, if I want to calculate the scalar components of B, I can do that using the same technique. This will be By, and it's opposite again, because this is our angle of interest, or theta. Bx is the adjacent side. The one tricky thing here is that since this angle is 56 degrees, I have to remember that this is left and make it negative in an ordinary coordinate system, because the cosine of 56 degrees is a positive number, so the output will be positive. The other thing I can do is just give that angle from 0 degrees. So let me explain what I mean there. All the way from 0 to here is 180 degrees. So this angle is going to be 180 minus 56 degrees. That's 122 degrees. So I can calculate Bx by saying that cosine of 122 degrees equals Bx over 26.5. And I can calculate sine of 122 degrees in a similar fashion. That's going to be By over the magnitude of the actual vector, 26.5. So Bx times the cosine of 122. Here, let me put a line here, separating that work from that work. A little sloppy. Hopefully you can do better on your paper. Oh, my bad. Bx equals, I got way ahead of myself. Bx equals 26.5 times the cosine of 122 degrees. And I get negative 14.043, which makes sense because it points left. So the calculator did the work for me and reminded me that it's negative. By equals 26.5 sine of 122 degrees. .47 and 0.473, so no need to round or anything, just leave it 22.47. So there are my scalar components of a vector with in the first quadrant and in the second quadrant. Now, let's see, this third vector, C, is straight down along the y-axis, so it's very easy to designate its components. Cx, we'll box this off, is equal to 0, because you can just, by inspection, by looking at it, you see that it doesn't go right or left at all. The angle is 270 degrees. And that means that Cy is just the magnitude of the vector. And I'm just remembering to make it negative because I can see it straight down at 270 degrees. I could put that into a calculator. I could do, Cx equals 0. I didn't like the way that looked, so I'm raising it. That's a little better, maybe. It's still not a great equal sign. I could put it into a calculator using like 31 times cosine of 270 degrees and 31 times sine of 270 degrees, and it will give me those answers. But it's just easier to look at it and say, that's the answer. Okay, I hope this is helpful. Remember, what one fool can understand, another can.